Good morning, here we are at the physics video lecture. Physics 105A video lecture 9. We're going to review a bit, but I'm going to set up that problem that we left off with last time. This is really getting into the great material, and we're going to turn this into a couple excellent homework problems as well. So here's where we are. We have conservation of energy, and then we learn to separate variables because the x dot is a dx dt, and we end up with t equals plus minus integral dx prime root 2 over m e minus u of x. You're just treating this thing algebraically, and we're going from x0 to x, okay? So that's the method that we used, and actually I set up as a homework problem to solve the basic free fall problem, okay? And we'll get back to that, but from here, since we have this dx dt is equal to, and we'll go ahead and solve for it, plus minus 2 over m e minus u of x. Okay. Since we had this expression as well, we were able to introduce the idea of turning points given a certain type of potential energy. So right under here, how about red? Right under here, we can imagine that we have a u of x, function of x. And this time I'm going to draw a non-symmetrical one, like that. Okay, let the x go out here a little further. Okay, so I deliberately made it, in fact, let's make it even less symmetrical. This is going to be a really classic one anyway, that we will see quite a bit of. Here's x, here's u of x. Suppose our potential looks like that. I'll write down what the function is for that. It could be a number of them. And this comes up against the axis as x goes to infinity. Right, so there's a potential with a local minimum at x0, I have to call it something, not to be confused with that x0, okay. So that's my local minimum now, and if my energy is equal to u of x, then this expression is 0, therefore the speed is 0, the velocity is 0. And so let's go ahead and have an energy here, E, and I'll draw the little dotted line across, and you can see that there is a minimum x and a maximum x between which the motion occurs. Okay, there's a minimum x and a maximum x. That's where the velocity vanishes. Those are the turning points. So yeah, it doesn't have to be a positive or negative energy. In this case, it's a negative energy because of where this thing is located. So then you could talk about an oscillation, and you could say, I will go between x min and x max. So for motion restricted to x min less than or equal to x less than or equal to x maximum, for that motion that's restricted there, you know, you guys can always just imagine a ball rolling between here, something sliding between here without friction, back and forth. That's what your oscillation is in a potential well. So for such a motion restricted like that, the period of oscillation by the way, this is not yet a harmonic oscillation. This is just a repeating motion as I'm describing here. The period of that oscillation would be t equals 2 integral x min to x max. This updates the one I wrote up the other day. Okay. dx root 2 over n e minus u of x. We're actually going to be working with this particular potential a fair amount this semester. Good. So that defines the period of oscillation. This is not a symmetric one. The other one I had minus a to a. Okay, we'll get back to that. But yeah, that defines a period of oscillation of just the motion back and back again, back and forth. And the plus sign was motion positive direction, minus sign motion negative direction. So good, you get the period of that motion. And what we're going to do now is talk about that general x to the nth power potential and apply all of this. That's what we were getting to last time. This just fills in a little bit more material. And in fact, we can add a note right here. The x minimum, x maximum are the turning points of the motion. Okay. Turning points. And you can't go beyond that because then this would turn into an imaginary quantity. Okay. So let's look at our next example, which we've seen before. So next, consider u of x is equal to b times x to the n. Okay. And we've already looked at this. I'll just draw a couple of them. With e equals b times a to the nth power. And yeah, if it's x squared, of course, it's just a parabola. X cubed, x to the fourth, those are flatter and flatter parabolas. So yeah, refer to the discussion we had the other day. I'll just draw one of these. Okay. So there is our energy corresponding to that. A and minus a. So we're going to do this integral now, very general one here. And we'll get some restrictions on n when we're done, okay? But we're just going to take it at face value. Okay. So that's x, that's u of x, and we can write here the period of oscillation is t equals 4, 0 to a dx root 2 over m. And what are we going to write? B times a to the n minus b times x to the n. We got rid of the absolute value because we're just restricted to the positive axis. Okay. Now this integral can't actually be done in closed form for just any value unless you actually get into some special functions. But what we're going to do is pull all of the physics out of the integral till we have t equals a physical quantity and then just a number. And this is a good exercise. So we've got our 4. I'm going to go ahead and pull out root 2b divided by m. Okay, we'll do this in a couple of steps. So root 2b divided by m. Now I have 0 to a dx root a to the n minus x to the n. And we can do one more step, and that is, you can't always do this, but when you can, it's very good to. We can turn this into a dimensionless integral, and I'll write under here in red, let y equal x divided by a, then dy is equal to dx divided by a. So that's going to be our substitution. So we still have the 4 over root 2b over m. Let's see what we get now. So our dx is equal to a times dy. We're going to have an a here. And our a to the n, we're going to pull out. So actually what we're going to do is our x to the n is going to be, let's just go ahead and write it out before we go to a. So I've got my dy. So dx is a dy. Got that. We'll do this in one more step. We have root a to the n minus x to the n, which is a to the n times y to the n. And our limits of integration are 0 to 1. X equals a, y is equal to 1. Okay, so we're going to work right underneath here. So now everything is there, and we really just have to write it out. So once more we have, here I can do this, t is equal to 4a over root 2b over m. Now you see I can pull out an a to the n divided by 2. Okay, pull out that power. So a to the n over 2, so that's a to the 1 minus n over 2. Okay. That's fair and square. And here now we are simply left with 0 to 1 dy root 1 minus y to the nth power. So this is as advertised. This is just a number between 0 and 1, so this entire integral just gives you a number. And if you try it for a couple values of n, you'll see that n equals 1 is easily done, n equals 2 is easily done, and that's about it. Okay. Other than that, you could look this up in the table of special functions, which I may actually assign. In fact, I will assign that. But let's first just kind of put parentheses around here and realize that what we've done is this is just a number, so all of the physics is out here. Okay. We can simplify this a bit if we want to, if we think it'll do us any good. But for the moment, there's really no point in simplifying it. Okay, we could simplify it, and well, why not? This will be it'll be the least distraction. But yeah, we have to keep the a 1 minus n over 2 out of the way anyway. So we've got 4 root m over 2b. I'm sure I can clean that up. 16 over 2 would be 8. Okay, we'll do that. And yeah, this is just the constant for the potential. So depending on the powers of n, you know, you have different values, different dimensions of b. Okay. Okay, but we definitely have to talk about a to the 1 minus n over 2. That's the amplitude dependence of these oscillations. And then 0 to 1. dy root 1 minus y to the n. Okay. Good. So what do we have here? Well, in terms of Newtonian dynamics, the period's always going to go as the square root of the mass. But if the mass were built into B, then again it wouldn't necessarily go that way. We're looking at the harmonic oscillator, that'll be the case. Before we talk about the harmonic oscillator, let's just investigate this amplitude dependence in particular, because there's a lot of physics in here. So example, here I'll just write this down. Period apparently depends on amplitude. Okay. So the period depends on the amplitude. Let's go through a couple of these numbers. N equals 1. That's essentially a straight line up there, and if you just took 1/2 of that, you would be looking at the free fall. Okay. N equals 1, we're looking at free fall. So for the case of n equals 1, what do we have here? Period is proportional to amplitude to the 1 minus 1/2, to the 1/2 power. Amplitude to the 1/2 power. That means that this amplitude is proportional to t squared. And, you know, we know that from our distance times squared law. So important note, h equals 1/2 g t squared, right? When we're doing free fall. So that t squared is just a general property of that type of potential. Okay. Now the next one is going to occupy a big part of this semester. N equals 2. So for n equals 2, that's the actual parabola. And for n equals 2, 1 minus 2 over 2, you have 1 minus 1, you have t is proportional to amplitude to the 0th power. T proportional to amplitude to the 0th power. Well, that's another way of saying the period is independent of the amplitude, and those are our actual so-called harmonic oscillations. Okay, so here, period, amplitude independent. And those are the harmonic oscillations that we're going to study at great length, okay? But not right away. So harmonic oscillations. So you see, we haven't gone any further than expressing, here, let me put this red box around here, expressing our time in this form here, and we're learning all this physics. We're learning all the physics because we're analyzing this expression. Like I said, this is just a number. So the third one I want to mention, n is equal to -1. Now, strictly speaking, for n equals -1, we have to monkey around with these constants a bit. We're going to do that next to get a consistent result. But in terms of this amplitude independence, that's still going to hold true. So we'll go ahead and use this n equals -1, and we get period is proportional to the amplitude to the 1 minus -1/2. So 1 plus 1/2, 3/2 power. Some of you may remember a law in which this holds, but we're going to work it out right now. So yeah, this is a great example because you see how much physics we can do, and we haven't actually even solved this integral. This is, another version of dimensional analysis, really. So we haven't done this integral, but we know it's just a number, and we've analyzed this expression right here. Okay, so the next example we're going to do, well actually let me assign a couple of things on this right here. So homework, this one you just want to do a little homework. So we've got this integral here, and the first thing we want to do is let u of x equal dx magnitude. That is to say, n equals 1, and then go ahead and complete the integration. It's roughly what we did before. That equals b of x, n equals 1. Okay, I'll just write there. Okay, that's the n equals 1 case. And complete the integral, complete the integration. Okay, complete the integration here, and then you'll just have this, you'll get your number out. That's not such a big deal. The next example, though, I'll put right under this. Here, I can erase this just for some room. What you want to do is look this integral up and figure out. What you'll find is it's expressed in terms of gamma functions. Okay. So this is something like the solution to this integral right here, 0 to 1 dy root 1 minus y to the n. So the general expression in terms of gamma functions. In terms of gamma functions. Gamma function. Right, that's a kind of a complicated expression, but it's just something out of a mathematical handbook, or who knows where you'll find it. So yeah, go ahead and look that up and write it down as well. So you want to have that part of your notes in your homework. So that'll be a gamma function thing. Okay, let me consult the clock. Okay, perfect. So I'm going to set up this problem now for this n equals -1 scenario, and we'll work through that. I'll set it up and you guys will finish it. Okay. So here's an interesting problem. Suppose we have an origin here, and that's a Newtonian center of attraction. So it's a Newton gravity attractor. And we have our little mass here, and we're going to start out at a distance L. So the problem is, we're releasing our particle m at time t equals 0, releasing it from rest, and we want to find the time it takes to be attracted to this Newtonian. So Newton gravity. Okay. find time of collision, we could call it. Here's a point where we're attracting by the inverse square law, and here we are, released from rest. If M is released from rest at t equals 0. So how long does it take? I'll just put a little note here. If we're just holding something above the table and want to find the time of collision for free fall, you know, we have h equals 1/2 gt squared, so that t is equal to 2h over g square root, right? So that would be the time of something falling in this room or outside. But if you're far enough away from the Earth, then you're subject to a different law. So yeah, just reminding you about free fall. This example here is, you know, we're standing here and we drop something, and that's the time it takes to hit the ground. And by the way, that's also good for, you know, top of a building or some distance. Actually, your Taylor expansion was going to tell you how good this is from that other assignment. But yeah, there's our problem. And over here we have F is equal to GMM over R squared. But we're going to say F is just equal to minus K over X squared. That's our one-dimensional version of Newton's law of gravity. So we have and we've done this one before, from the star expression here, and in fact I can, let's go ahead and put this on an axis now. So there's X, 0 is our center of attraction, and there's the point L, and we're going to be attracted to the left. Okay. So we already know that the potential energy is minus K divided by X. We did that the other day. Definitely include this in your write-up. All of these steps you want to include. So minus K over X. The graph looks like this. And again, we're releasing it from L. And in this case, if you imagine rolling a ball down this graph, it would just keep picking up speed, right, as it goes. And this is asymptotic towards the axis there. So we're going to set this integral up, or not exactly this one, but the quadrature one, for this function here. Good, so we're released from rest. We release an object from rest and it falls into the center of Newtonian attraction. So let's go ahead and write down our integral expression. And as many times as you have to practice, this is fine. First of all, plus minus dx prime 2 over m e minus u of x. Okay. x0 to x, okay? So remember, this just comes from conservation of energy. So do this as there it is, the square root. Do this as often as you have to. to get to that point. Our question is, what are our boundaries of integration? So we have here, E is equal to minus K over L, since I chose L to be that distance from which we're releasing it. So E is equal to minus K divided by L. And we have to go into this integral now. X0 is equal to L, and X final, I'll just write final, is equal to 0. So now, we'll use capital T, or we'll use T, namely the time that it's going to take now, so it's not variable time. So what do we get here? We've got this plus minus root dx prime 2 over m. Energy minus k over L minus u of x, so that's minus a negative plus k over x square root, and we're going from L to 0. So here you can see what I was talking about, that formalism. We're moving from right to left on my coordinate system here. So that's why we're going to pick the minus sign right here. We're going to pick the minus sign, but we're going to reverse the order of integration here. So that will be 0 to L. We'll reverse the boundaries. And then we've, again, got that dx prime 2 over m k over x minus k over L. See, since x is always less than or equal to L, this integrand is all right. And I should leave it here. I'm going to leave it like this and give you guys some instructions. So you want to keep doing this. As a homework problem. And you'll see, it's such a great problem. You want to set it up at the very beginning and run through the whole thing. Do that integral again. Starting here, set this up. Now, in terms of doing this, you want to make it dimensionless again. So, important note, turn this into a dimensionless integral. I'm tempted to do it myself, but so first turn it into a dimensionless integral. All the physics will be out front, and then this integral you get is going to be pi or pi over 2 or 2 pi or something like that. Okay, interesting integration in itself. You can do it by substitutions, trig substitutions and stuff. But yeah, you have to first turn this into a dimensionless integral. And I'm just going to point out what you're going to do. You're immediately going to have that 1 over root 2 over m. You're also going to have a k. So you're going to have 1 over root 2k over m right from the get-go. Then when you get a dimensionless length, let your, say, y equal x over L, just the way I did y equals x over a. When you make that substitution, etc., all the dimension quantities will come out, and you'll even have that t is equal to, t will be proportional to L to the 3/2 power, just like we had up here. Did I erase it? Yeah, of course. Just like we had before. We'll have that t proportional to L to the 3/2 power, some other quantities, and then you'll just have to do the integral. And this is an important result. We're going to hold on to it And later on in the semester, when we're talking about Kepler's laws, we're going to find that this result is going to be a limiting case of Kepler's laws of elliptical orbits. You could say it'll be the straight line limiting case. Very interesting result. So, like I said, turn it into a dimensionless integral. You know, this thing comes out right away. You can see that the y equals x over L is your next substitution. Should work out really nicely. Once again, I will consult the clock. Yeah, okay, that's a major homework problem. Started up there, whole discussion. I think you guys will really enjoy it. Like I said, some trig substitutions for the integral, and I'll put a note here as well. This result can be compared to Kepler's third law when we get there. So that'll even be a great moment too. And that'll be towards the end of the semester. Okay, that doesn't quite wrap this up, but it's a good start. Let's see. I'll add a little bit in terms of these potential energies functions. Maybe this is a good place to. Actually, this is a good place to. This is a good place to stop. So yeah, enjoy these problems, and we will talk again next week. Okay, Monday's a holiday, as a matter of fact.